Okay, so Friday, another Zoom lecture, but hopefully we will be back, not hopefully, for sure, we will be back to in-person classes as of Monday. Okay, thank you for being patient and understanding and attending the classes online. All right, so let's get started with what we finished last lecture. Last lecture, we got to 4.3, the steady state response of a rotating unbalanced system. Again, this is a system that you've seen it before, but without damping. This time we add damping. So we have a system with mass M. Including that mass M, there is MR. Right. So again, I emphasize this MR is part of the M. Or let's say this box, the total mass, including MR, is M. All right. So like if you put the whole things, this box on a weight, the total mass is M. Inside that M, MR has an imbalance E, which is rotating with speed omega. And this omega, let's assume it is in radian per second. So then all the unit works out. The base is fixed to the ground, all right? And we selected this X to be our coordinates, the absolute coordinate. We as an observer attached to the ground. So in this system, as we had before, because of this MR, we have this centrifugal force, right? And this centrifugal force, I can slide it down to the center because it's going to apply to the center. Right, so I have this centrifugal then force. So this centrifugal force, we know how to calculate it. It is MR, the unbalanced mass, or the rotating mass. That's why it's called MR, E omega squared. All right. So now, if I look at this system, there is no motion in horizontal direction. I'm only interested in the vertical direction. So why not? I find the component of this force in X and Y direction, or in the vertical and horizontal direction. So let's quickly do that one. If I find it in the horizontal direction, let's say I would get this load. Let's show it by maybe, let's show it by different color. Let's show it with green. Oh, not a good color to be seen. Stick with the pink. All right, so this one is going to be MR E omega squared sine theta, right? The component of this load. Of course, it has other component, but that other component doesn't do anything for us in terms of vibration. Like the horizontal one will be MR E omega squared cosine theta. But it does not create any vibration. This vertical one, as you can see, as this mass is rotating, it creates vibration because it's at one moment it is up, another moment is down. And the amplitude, of course, is changing because this angle is changing. Remember, this theta now is a large angle. It's 2 pi, right? It can change from 0 to 2 pi. So you cannot substitute it with like approximate it by 1 or 0 or sine theta equal to theta. It's a large value. So this is our free body diagram, and obviously I have the forces here from the spring and from the damping. So the spring is Kx resisting the motion because of the direction I picked, it is x, and this one is Cx dot. Now, you know what will be interesting? Let's say the same setup if also you have a base motion. Can you solve it? Absolutely, yes. You just need to draw the free body diagrams. It's just combination of two problems, rotating mass and base motion. Now it reminds me that can be a good question for your exam. Okay, give it some thought. So, but now, for now, let's just focus on this one. The base is fixed. Since the base is fixed, I only have Kx and Cx dot. So my free body diagram is complete. And now I can write down the equation. Sum of the force in x direction is m x double dot, because my acceleration is x double dot. So what do I have? I have that pink load, which is positive. So it is mr e omega squared sine. And let's substitute theta with omega t. Remember, since it's rotating with the speed omega, and the questions should say that omega is constant. So omega is constant. Then theta always is omega t, because we like to have it as a function of time. So that's a positive force because it is in x direction. Minus kx minus cx dot is equal to mx double dot. Remember again, this is the total mass m. So we already included these mr in this m. The whole box is moving ups and down, has acceleration x double dot, including that little mr inside. So I now let's clean it up and write it in a form that we know what to do with it. Mx double dot plus Cx dot plus Kx is equal to mr e omega squared sine omega t. So that's an equation that is familiar for us, and we know how to deal with it. So in this equation, the value of mass is m, the value of c is c, the value of k is k. You may solve another problem that this value change, but it doesn't matter. As long as you have something as a coefficient of x, you consider it as your stiffness. The only things that is different is now our F0. Now F0 got this new form, F0. So I will write my equation. Let's do them over here. So as a standard form, I know for a standard equation, we learned that xt, the steady state response, is x sine omega t plus phi, which for phi, we have a formula. We know what is phi. This is omega, right? Is the forcing frequency, which happened for us to be omega. And in this scenario, our forcing frequency is in fact the rotating speed. All right. So x has also formula. That formula we learned it is equal to F0 divided by K, the square root of 1 minus omega divided by omega n squared plus 2 zeta omega n squared. Now I remember why I memorized all of these formula. When I was a student, at that time, there was no concept such as like formula sheet or cheat sheet. We have to memorize everything. Everything's actually every details, every formula. Yeah, there was not such things as formula sheet. Even calculators there were calculators, but no graphic one. And they were very expensive. Like few students could afford having a calculator, like a good one that you can do like engineering calculation. Anyway, but nowadays everybody has a laptop. She's amazing. So this is our formula, our standard formula. As you can see, nothing is different than the original formula. Phase, if you are interested in knowing, which we are not usually, it is tangent inverse of, don't forget the minus omega over omega n. Oh, sorry, 2 zeta omega omega n. And 1 minus omega omega n squared. So now let's focus on x. See how x now turn out for a rotating system. I substitute f0 with the value that we just found, which is mr e omega squared divided by k, and then this one over here, plus 2 zeta omega omega n squared. All right, as you can see, I haven't changed anything. I just substitute my f0 with the value that, as you can see in this equation, is now a new f0 for us. So now a little bit of manipulation. Like always, I multiply it by m, I divide it by m, and this m over k give me omega n squared in denominator. So I would get an equation which is x m e m r equal to omega over omega n squared 1 minus omega omega n squared plus 2 zeta omega omega n. Oops, sorry. I need more room here. Let's move everything's a little bit to the left. And this guy is squared. What is that? All right. So let's stop here, take a moment and see if I haven't done any calculation mistake, right? This is m over k, which gives me omega n. So over here, I wish to have omega over omega n. So I move everything to the left side. So mr multiplied by e, I have it over here. So that's correct. I have an extra m over there, which comes down over here. Seems to be correct. So I'll give you a moment if you want to take notes or just absorb to see what happened, right? We draw the free body diagrams. We write the equations. The only difference between our standard form and this form is the form of f0. We substitute few things and manipulate the equation. So we got this form. Now, in this equation, we call this guy the magnification factor. So m for magnification factor, m, or some people show it by mf, is equal to x m e m r, which, as you can see, it doesn't have any unit, right? X and e, they cancel out. M and mr, they cancel out, right? No unit. So magnification factor, it always doesn't have any unit, and it is equal to omega over omega n squared 1 minus omega omega n squared 2 zeta omega omega n squared. All right, so new form of magnification factor. And like always, we like to plot these things and see how it looks. Of course, for simplicity, we start with no damping scenario. Let me make this one better. This is omega, and this is like that. Better. Okay. So any questions so far? I'm going to stop to see if there is any question in the chat. No, chat is quiet. If you guys have any question, feel free to unmute.
Hi, Ahmad, I have a question.
Yes, Apol, go ahead.
Yes, so in your free body diagram, you include the centrifugal force. It always confuses me, like when to take centripetal versus centrifugal force.
All right, so that's a good question. So in dynamics, probably you've seen when you have a rotating, maybe you should unmute yourself because there is an echo. I can go over that one later with you with more details, but in general, we say when you have, let's say, rotating mass, rotating with the speed omega, all right? So when we draw the free body diagrams, we say it has two acceleration. One is AN and one is AT. Each AT, in this case, we don't have any ATs, R alpha, and AN is R omega squared, right? We call them the normal acceleration and tangent acceleration, correct? Now,
yes,
when you draw the free body diagrams for this one, right? But let's say for just this mass, you say this mass has a tension that apply to it T, like this link, like a tension T, that's the only force for this mass, all right? And, oops, my pen, what just happened? Sorry, I just closed these things. Okay, we're back here. All right, so we have two directions for this one. This is our free body diagram in dynamics. As we explained, this, we call this one the acceleration diagram, and this one the force diagram. So looking at this diagram, I can write down the Newton law. Sum of the force must be equal to ma in the direction of n. So in the direction of n, I have one t, right? And I have one m multiplied by an, which is r omega squared. Okay, so far, are you agree?
yes,
Okay, so this is like the good way or the standard way that we do these things, right? However, when we like write this equation, as you can see, I said T is equal to mr omega squared. So I said that there is a tension in this T, which this T, the force, is equal to mr omega squared. So a guy called D'Alembert said, why not we just show it with this diagram rather than drawing two diagrams? We show it by one diagram showing the force and one diagram showing and just the mr omega squared, and we call it the centrifugal force. Okay, so and in over here, this is what we will do. We say on this system, we don't open up everything. Only things like we are not interested in the force going to the joint O and that things. We say this mr create an external force, which is a centrifugal force, and it comes from this normal acceleration, which we write it as mr omega squared. So this is a brief explanation, but I'm happy later to explain it if it still is not clear for you. Okay?
It makes sense. Thank you.
All right, no problem. Now let's return back to the vibration stuff. So in vibration, anyway, always you look at the centrifugal force, and that one acts as an external load for you. So let's attempt to draw this M, this magnification factor, quickly. So this guy then is M, and we know M for us means X, M, EMR, or that big things, which we like to plot. And this is omega over omega n, which some people just show it by R for simplicity, like this ratio. So we suspect that something bad may happen at 1. So always we draw a line at 1. And we also suspect from our base old experience that there might be something also happening at when it's m equal to 1. And sometimes that is square root of 2, right? So for simplicity, if I start with the case where zeta is equal to 0, then we have the m that we know from the past, and it confirms our equation is correct. And again, it has positive and negative, but only we care about the positive, right? When I don't have any speed, this time it is 0. It does not start from 1. And obviously at 1, it goes to infinity. And when omega over omega n getting to infinity, so you can see from this equation, I have omega over omega n squared in denominator and in numerator, in numerator and denominator. And so both of them goes to infinity, then this graph has to go to 1. All right, so that's for a case when zeta is equal to 0. For other cases, so just this is a hand drawing. It looks like something like that, but all of them again go back to infinity, because if you look at the whole equation, you have omega over omega n squared on the top and omega over omega n squared in denominator. So infinity on the top, infinity at the bottom. So they have to go to 1. So let's say this is, pretend this is 0.2. We just made up these numbers. So this is then our magnification factor for this scenario. All right. So always when I'm at a very, very large omega rotation speed, I have still one magnification factor. I cannot get rid of everything. So m is equal to 1. And it seems that's the best scenario. The faster my system rotates, the less I will see the effect of the rotation. All right, I'm gonna stop here. Let's see if you guys have any question for this graph. We're good? So I'm gonna stop here. Rather than solving this example, I'm gonna go to this slide, which is after example 16, and you don't have it in your note. I just added 5 minutes before the lecture. As I promised, I found the, like I copied the graphs from the textbook and put it here. So you have it as a reference. So if later you can copy, I will post it today. You can cut this part and put it in your note, copy and paste it. Or if you're using it now, you have it as a reference, right? And I summarized here all the magnification factor that we talk about so far, right? So let's go one by one. And the first one, M, right? All of them is M. Is for the simplest case that we had, a harmonic excitation, Ft, and we only were interested in knowing X. Okay, so we said M is X over X0, which X0 is F0 divided by K. So that's our first formula that we have. So anything particular about this one? We said something will happen at omega equal to 1, but slightly before omega equal to omega 1. However, we didn't pay too much attention to that things because it's very, very small. And at the peak, we approximate the maximum m is 1 over 2 zeta, like an approximation. And it is happening at 1. Again, it's slightly before 1, but because it's very, very small, usually with small dampings, we just pretend it is at 1. And x0 is f0 divided by k. What is f0? Like this ft, if you remember, it was a f0, a number, sine or cosine omega t. So the rest of these parameters, you know how to calculate them. All right. So you have omega n, you have zeta. So omega n is the square root of k over m. And zeta has a formula is c over 2km. I just substitute c critical with 2 square root of km. Now, the question came up last lecture. So this is for a standard system when you have one mass, one K, one C. Now, let's say you solve a different problem, which we will, and also in your practice problems, there are many. So remember, the value of the formula will be exactly the same. It is only the value of K, M, and C changes, right? Let's say you solve a new system, and for some reason that new system turned out to be M L squared x double dot plus, or even theta double dot plus maybe K minus, just make this up, maybe KA minus M over L, maybe even the unit doesn't seems right, theta plus something which has C in it, theta dot, equal to F0 sine omega t. So for us, this is K, this is M, and this is C. All right, so just something to clear. No matter what equations you have, you look at the coefficient for M, K, and C, and you will find your value for omega n and zeta. So that's the first magnification factor that we learned, right? So important things about it then, at 1, when omega is equal to omega n, you have 1 over 2 zeta, and it goes to 0 and start as at 1. Like this is when you have only a static, no dynamic force. Like omega is equal to 0. So for it to make sense, if this one should be F0 cosine omega t. We use cosine omega t. So that's one thing. Right? I'll come back in a moment to this one, and I'll explain some extra things about it, which is important. The second magnification factor that we learned was just now, 5 minutes ago, was for rotating system, right? Over here, I draw a rotating system for you. This is the rotating system. And this is the magnification factor formula. And this is the accurate graphs. As you can see, again, at 1, system is unhappy. And again, everything's go to 1 at infinity. So that's magnification factor for this scenario. So this is M. So the next scenario was for a base motion at the bottom. The base motion has 2 things that you need to remember. One is when I'm interested in magnification factor for X, I'm interested to know how much X is moving. What is the magnitude of vibration for X? So I define my magnification factor as X divided by Y. So my magnification factor is the ratio of X and Y. Remember, this Y is, again, the displacement has a capital Y sine or cosine omega t. All right. So, and this X is, let's say this is xt. It's always a function of time, is X sine, in this case, cosine omega t plus phi. Now we have a damping, so we have a phi. But all we care is about the magnitude, X. The ratio of X to Y, the graph looks like that. In this graph, like always, at 1 system is unhappy, and at a square root of 2, my magnification factors is equal to 1, which we said it has a meaning for us. Magnification factor equal to 1, it means whatever my base vibrates, I will get the same magnitude for mass M. If it is vibrating with the amplitude of 1 millimeter, I would get 1 millimeter. So that's when M is 1. And we said we wish to have to be after this square root of 2 because it means less vibration. And speaking of base motion, again, I draw it over here on the right end in this corner. We also are interested to know how much force transfer to the base. We call this one the transfer force. Transfer force to the base. And we somehow the formula turned out, because we want to make it without unit, divide by ky. So ky is our yardstick to compare how much now force gets to the base. So if I don't have any dynamic force or any dynamic motion, if I only let's say deflect the base by capital Y, so most likely my base, it gets a force of K multiplied by Y, because damping, when there is no motion, doesn't apply any force. So I compare it with how much force is increase or decrease. And somebody asked, I guess it was Apple, that are we always between 1 and 2? And I said, I'm not sure. And it seems that when we plot the graph, no, that damping, at higher dampings, so the graph actually is going to get bigger than 2. So this is the conclusion that, again, we made. At a square root of 2, we are getting the magnification factor of 2. So remember, this is 2, not 1. All right. At the square root of 2, M always is 2 for all the cases. But after that and before that, we talk about it that these magnification factors become smaller and larger. But at the square root of 2, it's always is equal to 2, not 1. Right? Unlike this one, like for this scenario, M is equal 1. At, oh, sorry, this one, we don't have any things. Oh, here. At the square root of 2, M, which is X equal to Y, is equal to 1. Right? This M, this one is Ft, like Ft divided by Ky is equal to 2. It means I get twice the force of Ky, the static force. Anyway, so you don't need to, again, memorize them. You just need to know these things are there and try to understand these graphs. Now, an important question somebody asked last lecture, and I promised to explain it here. They asked at the very end of lecture, I guess after the recording was done, that are these graphs are important? Yes, they are. Of course, for exam, you need to know them. There might be question related to these graphs, but they meant more like in practice. In practice, let's say the first graph, how people use the first one. Let me write it down here in practice. But that's true. I'll just explain for one of them, but that's true for all of them. So you get the idea in a moment. So in practice, people usually do tests and get a graph which is not as nice as this one, but looks like similar to this one. So on X, they have omega, and on Y-axis, they have like the value of X because they measure X. We don't measure M. M just mathematically, we define it, right, as the ratio of X over F0 divided by K. So they do a test and they get a graph that may looks like this. Right? So, and now, like they do tests at different points. Remember, this is the speed. Let's say they have a rotating unbalance, they are applying a load, something. They change this omega, and when there is nothing, they are at 0. They should get x0, which is simply f0 divided by k. Right? And then they increase the speed or the omega, and they get a new value for x. They repeat the test, and at some point, they realize the system gets crazy, and they know this is where omega roughly is equal to omega n. And this is when they quickly, they find out what is their value of natural frequency for this system. Because remember, in complex system, you don't actually have a nice K and nice M that you can divide them and find the natural frequency, right? You have to do measurements, and you do your measurement and you will see there is a peak. And after that, you realize that, okay, the vibration becomes smaller and smaller, and then eventually it goes very small, but you don't have probably the tool to go that fast, but you realize the trend. All right, so this is a typical graph that you would get in practice. So from this graph, obviously you can estimate omega n, and when you have omega n k over m, you can estimate your mass system because already from this portion you can estimate your stiffness. And what else? Well, we know this peak, like this peak over here, right? We know this one is not M. Remember, this one now is M multiplied by X0. Remember the definition of, let's call this one M max. So let's call this one, sorry, X max. Okay, so I'm going to write it down here on the top. We know X max is equal to M max multiplied by X0. Do you agree? Remember our definition of M? M over here was X over X0, and X0 was F0 divided by K. We have it over here. So X max is equal to M max X0. So they managed to measure their X max. They know their X0. Voila, you have your M max. And M max has a formula. M max is 1/2 zeta. Remember, this is over here, 1/2 zeta. So from here, you can find zeta. And from here, obviously, you can find your damping. This is how people find their damping, their stiffness, and their K. And you may say, who cares about the system damping, stiffness, and mass? Well, they care because they want to reduce the vibration. They want to do something about it. Okay? So I give you a moment to absorb what I just explained, because this is important. This is actually what people do in practice. They do their measurement, and this is the way they use these graphs. At the peak, they know their omega n. At the peak, they know it has something to do with 1/2 zeta, and done. All right. So while you are taking notes, I'm going to draw that graph one more time. Or no, we can just use it because there are some other people. Let's call it second method.
Sir, could I ask you a question?
And yes, please go ahead, Ansys.
When you have harmonic force,
Right.
is P kind of slightly above a ratio of 1? Harmonic force, could you, like at the bottom right, do you notice that the peak is slightly off 1.0? Is that actually true?
Okay, so for the bottom one,
Yeah.
the peak is a slightly after one. Yes, that's correct. And
Okay.
even like for the top one, the peak is a slightly before one.
Mm-hmm.
Right? So this one is a slightly before one. This one is a slightly after one. The first one, we managed to find it. We take the derivatives. You remember, we take the derivatives and we managed to find it. It was not that one. Like a slightly before that, at this point, which this point, I'm gonna write it down over here, was 1 minus 2 zeta squared. Okay, and yes, you're right. This one is slightly after one. And you can find it by taking the derivatives. I can tell you, but I don't want to confuse you with lots of equations. Okay, does that answer your question, Ansys?
Yeah, thank you.
No problem. All right, now let's talk about the second method. Second method, like again, this is more based on practice rather than like actual theory. Let me draw the graph again, so that one doesn't get messy. This is X, and this is omega over omega n, or just omega, sorry. So remember, in practice, this one is omega, not divided by omega n. We divided by omega n on those graphs because we wanted to make everything without unit and make them nice. In practice, you just increase the speed. Later, you may plot it divided by omega n. So the way that it works also is you find your peak, and then let's say the peak is X max here. And people say that you should not only avoid the peak for your machine, also you should avoid X max divided by a square root of 2. So if this point is x max, this point is x max divided by square root of 2. Where did that square root of 2 came from? There is some math. You can take the derivatives. They realize in practice that this is like a critical region. You should avoid getting close to that. Like there is a bandwidth to avoid. And this has actually a name. It is called half power. So people call it. Sorry, let's back. So it is called half power. I know it is not half, but because in the actual formula we have a square, when they divided it by 2 and then everything's simplified and approximate, it gets out to a square root of 2. So x max divided by a square root of 2, which is called half power. And this range is called delta omega half power bandwidth. These are just technical names. I want you to remember them because actually when you go out in practice, this is what you will see a lot. And this is a range that we recommend that you should avoid these half power bandwidths. And as like a quick formula, rather than going through all these m1/2 zeta, people found that you can estimate your damping by just dividing these delta omega over 2 omega n. All right, so let me put it inside a box as an important formula. So zeta, you can estimate it, not again an actual value, by dividing this delta omega. Where can you find delta omega? So you know your x max. You come down by x max divided by square root of 2. So to the point x max is square root of 2. Wherever it's like cross the graph, those are the range. And it's not symmetric. On this graph that I showed, it looks like symmetric, but the graph is not symmetric. It can be anything. Like symmetric, I mean around omega n. It's not. And this is our omega n, right? It's our natural frequency. Okay, so two methods then in practice, how people use these graphs. I hope it's clear. Let me check the question in the chat. So from Jenny, this is exactly one of the many things in vibration diagnosis. In vibration diagnosis, I will talk about it again toward the end of the course. People use accelerometer. They put accelerometer on the machine. They do measurements. It depends on many things. You then get these graphs. You realize if you need to add mass, if you need to add a stiffness, or if you need to add damping. But as a rough estimation, let's say if you have a motor, for example, something that you can change omega, the speed, then yes, you try to get this graph. Let's say you have a pump and it vibrates a lot and you want to do something about it. So quickly you draw this graph by changing omega. You start from 0, 1, 2, plot this graph, and then try to find this delta omega. How can you find this delta omega? So you know where is the peak. So you know your x max. You divide it by a square root of 2. And then on this graph, you have your bandwidths. And then you recommend to the owner that try these bandwidths. That's call it a bad zone. Right? This zone, which I'm highlighting by red, it's a bad zone. So the speed of these things should be either below or after that point. And in theory, we say yes, only you are in trouble if you are at omega n, that's the peak. But also we want to avoid getting closer to that peak as well. I hope that also answered your question. Okay, so before you guys leave, 3 important things. On Monday, we will be back in-person classes. Hopefully nothing bad will happen to me. And the tutorial today will be on a very new topic, 2-degree freedom system, but very, very basic question. Try to attend. I asked the TA just to draw the free body diagrams and develop the equations and show you the difference between a single degree and 2-degree. Intentionally, I set it up before I teach the topic, which is I will teach it next week, but I want you to go there because next week I'm not gonna spend time on like how to write it in a matrix form. So try to attend. It's very simple, but try to attend. And also you need that for your lab. For the lab, it is something that, as I said at the beginning, you will do it at home. It's an experiment that it takes probably half a day to complete, and maybe a day or maybe 2 days, depends on you, to write the equations and complete it. But something that takes time is finding the tools. There's not too much tools, but the rulers and the thread. I suggest take a look. Try to, when you go next time to the hardware store or to a dollar store, buy these things rather than wait and realize that everybody, because you need like a ruler, 1 meter ruler, and maybe you go next time to a staple. This class, there are how many? 100 students. Other class, there are 80 students. So 180 students, I'm sure a staple doesn't have 180 1-meter rulers. And then you have to travel to Abbotsford, Staples in Abbotsford, to find the 1-meter rulers, all right? So try to get the tools for the lab. So that's one tutorial I mentioned, and we will be back in person. Please review what we just studied today. This slide that I'm just showing it here is an important slide. It has like things that happen in practice. And also the 4 magnification factor that we discussed for a harmonic motion, for base motion, and for a rotating system. And please spend some time on these 3 examples. This is super simple, 14, 15, and 16. I will solve them on Monday. And then on Monday, I will spend also some time on how people solve the equations in MATLAB or in other software when FT, the excitation force, is not harmonic. So far, we just talked about harmonic force, right? And if we are done, then it means we are done with the single degree of freedom system. Okay, have a nice evening, Friday evening and weekend. I can stay in a room if you guys have question, and I'm happy to answer your question. Otherwise, have a good day.
So I want to ask you something about the accelerometers question.
Accelerometer question, all right. And
the free body diagram. Why is the top spring force named as kx and not kx minus y?
well, if you remember, we said, just as a practice this time, let's consider this x, the motion between M and the frame, not the absolute motion, right?
Mm-hmm.
So the relative motion. So this x is relative motion. So Now let me ask you this. If I assume X is my measurement from this mass M to the top of this frame, so does it matter how much I move this Y? Like if I move it 1 meter, this X still will be the same, right?
So the frame of reference for X is the mass itself.
That's correct. Yeah.
And in that case, where does Kp come from? Because if you excite the base, then
So if you excite the base, this M probably goes ups and down, right?
mhm.
And now we said, let's assume this piezoelectric material. It's a material, it's a flexible material, and it acts as like a spring. And that's why we said it has a stiffness and damping. So on the diagram that I showed on the right side here, so the base of this force is moved with YT, which is the base of motion, and the mass is moving with XT, which XT, we call it the relative motion. That's why when we derive the equation of motion, our acceleration should be x double dot minus y double dot.
Mhm. And where does Kp and Cp come from? Oh, the piezoelectric material.
Yes, the piezoelectric material, and should be given to us by, let's say, the question. However, this will be done by the manufacturer of the company. They do all these things. At the end, they gives us just one number. If you purchase an accelerometer, you will see it tells you that for each millivolt output that you get, multiply it by this number G, right? So you go, you do your test, and let's say you will get a value for X, which is, let's say, since it is vibration, you will get a value for X, maybe a graph of something. This graph of something, which is over here, is time. The y-axis is not acceleration, it's voltage. Like any accelerometer that you purchase, the output is a voltage, okay? And this voltage, the manufacturer, the accelerometer, when you purchase it, gives you a number. It's called they say the actual acceleration is equal to the voltage that you measure, multiplied by this number, which is sometimes like a 2-3 digit number, G. Like they give you like this number. All right?
Okay.
Does that make sense?
When we consider Kp and Cp, we consider it relative to the absolute reference.
That's correct.
Okay. Just because it's a piezoelectric material.
Because it's a piezoelectric material, it's a flexible material, and we assume it has a stiffness and damping. Yes.
Okay, sure. Thank you.
All right, no problem. So any other question?
Actually, I have one more, sir. When we were talking about those graphs today, you wrote down zeta equals to the half power bandwidth over 2 omega n, the natural
That's right.
frequency.
Yes. That's an
And this is
estimation
an
of zeta. This comes from practice, not for practical measurement, not from theory.
Okay, but it's an actual usable equation that we can rely on.
Yes, that's an usable equation. Actually, for either if you use that formula, like the second method, or the first method using the M max here, you would get approximately the same number, very close.
And
Because
for M max, oh yeah, so M max roughly equals to 1 over 2 zeta.
That's correct. And that's, if you recall, a few lectures ago, we prove why it is equal to 1 over 2 zeta, roughly. That's like this long formula, what we estimated 1 over 2 zeta.
Okay, sure.
All right. And by the way, why your name shows Alberto while you are ANSYS?
I'm on Alberto's computer. It's the two of us.
Oh, that's why.
Hello, Ahmad.
Hello, Alberto. By the way, I changed your team number. Okay, let me stop recording.
Okay, thank you.
Stop recording.